Okay. Oh, good. Yeah. Sayan,
Yeah,
please go ahead.
yeah. Hi. Hi. Thank you first of all very much for having me today. I am Shan. Today I'm excited to present our recent work on efficient codec tokenization approach for VLMs. Uh, just a quick introduction about myself. I'm a second year PhD student at Stanford with Professor Eero Armenia, the Gradient Space Research Group. Before starting my PhD, I was a master student at ETH Zurich in Switzerland, where I was with Mark Polifay at a Computer Vision and Geometry Group. Apart from this, I'm an incoming intern with Waymo Perception Research this year. Last year, I interned with Microsoft and Qualcomm, and I also have some experience with my Mercedes. The project that I will be presenting today is from Microsoft. A little bit about my overview of my research trajectory. So the overarching theme of my work is multimodal understanding and spatial intelligence. So the first work was SG Aligner, where we were trying to do 3D scene graph understanding, 3D scene graph alignment for spatial understanding. And then we moved on to do crossover at CVPR 2025, where we were trying to get rid of the so for cross modal retrieval and multimodal understanding, we're trying to get rid of the scene graphs because scene graphs are very difficult to obtain in practice. Then at NeurIPS, last year we presented Guide Flow 3D, which was on guided 3D asset generation using flow matching. So it was a style transfer method across multiple modalities. And the work that I'll present today, CoPE, where we try to efficiently process video for language models, which is fundamentally about understanding temporal dynamics in visual data. So CoPE, the full name of the paper is Leveraging CoPE-VideoLM, Leveraging Codec Primitives for Efficient Video Language Modeling. This is a joint work with Remy, Andra, Mark, um, Amadi, and Mihai from Microsoft, and EO is my advisor. This was partly done during my internship at MS last year. First, let me start by motivating why video language models matter. So from question answering to robotics, only images are not enough. So video LMs represent a major advancement in multimodal AI. They enhance VLMs with temporal reasoning, which allows us to understand how visual narratives, objects, actions, and relationships evolve across video sequences. First example is video question answering. So this is very similar to a ChatGPT-like setting, or your favorite Gemini setting where you upload a video, go ask Gemini what is happening in the video. The second is more of a real world setting where you're trying to ask the trying to see if agents can understand sequential actions to interact with the world. And lastly, video retrieval. So video retrieval is basically finding relevant video content based on textual queries. So this could be your favorite social media like Instagram, YouTube, Facebook, anything. So the importance of video language models extend beyond these technical capabilities. So they sort of represent a fundamental step towards AI systems which perceive and reason about the world more like humans do. We want to process information not as like disconnected snapshots, but as continuous, meaningful experiences. So the goal here is to build models that reason about temporal dynamics, not just static snapshots. And how do current video models actually process the video? So usually it would be something very similar where you are sampling a keyframe, you encode the full image and feed all tokens to the LLM. So just to show you as an example, this is a hockey game in, I think, ice hockey game in Canada. So what you do is you sample fixed number of frames regardless of video length. So let's say you sample 8 frames, 16 frames, 64 frames. I mean, these days, the biggest models can go up to 384 or 400 frames also. So then you pass these frames through a vision encoder, which is usually Siglip, which produces vision tokens. Then you ask a question, and the question goes through a tokenizer, and these are the vision tokens and the language tokens are concatenated with language instruction and fed to the LLM, which generates the answer. So the fundamental problem here is that every frame is fully decoded and tokenized with the same token budget, completely ignoring the inherent sparsity of video. This is sort of a key issue that we'll address today. So sort of to put this in perspective, video language models have a maximum context window that limits the amount of information which can be provided as input. So this is not only a training artifact, but also related to hardware constraints, right? Because larger context windows mean you need linearly more memory and quadratically more compute. So what do we lose what is the actual cost of this brute force encoding? So to give you an example, what gets lost in this sparse keyframe sampling approach? So let's say this is a video that you have. And these are all the frames of the video. So, and you are sampling only the blue ones. So that means anything that in the any event that happens in the gray ones, you miss that event. You either miss some macro events, that mean the example that I give, key events happening between sample frames, or micro events, which means that fine interactions that is below the sampling rate. Just to give you an example, that 1 hour video, even at 1 FPS, is 3600 frames, and you only end up sampling about 64 frames. So that means over 98% of the video content is simply discarded. So now what is wasted? So let's try to so this is an example from perception test, which is a perception based data set. So here you're seeing a cooking video, somebody trying to make tea. So video also has high redundancy. So high redundancy between consecutive frames, even when downsample to 1 FPS. So you can see here only the hand is moving. So using the same token budget for each keyframe is simply suboptimal, right? So the key information here, key insight is that here that information's content scales with video duration, but the context window doesn't. So we sort of need a smarter representation. But the thing is, video codecs, which is a decades-old field, already solve this problem. Standard codecs like MP4, H.264, AV codecs already solves this problem for us. Because they only store what moves and what changes, not every single pixel. Let me give you a bit of primer about video codecs, because not everybody might be familiar with codecs. So let's say you have the same video where somebody's trying to make a sandwich. You can see here is that this is an entire video where only the hand is moving. The background is mostly static. So the first frame is encoded as an I frame or an intra-coded frame. This is the full RGB image, which is encoded independently. This serves as a reference point. The next frame is a P frame. So all the next frames are P frames. And the P frame is only storing changes from the previous frame. So only storing changes, you can think of these as git diffs. These only only stored like the motion vectors plus residuals. And the distance between two iframes is called group of pictures, or GOP. So essentially what it means is that GOP structure and the length control the trade-offs between compression efficiency, quality, and the capability for random access. So in a typical streaming setup, Codecs provides keyframes every 5 to 10 seconds, either at fixed intervals or when last scene changes are detected, encoding only the changes for remaining frames. The thing is, this group of pictures is basically you have one iframe, you have the rest of the P frames, and then you have the next iframe only when there is enough change. Now, what are motion vectors? This is basically block-wise optical flow. And the residuals are difference after motion compensation. Instead of me telling you in theory what it looks like, I will show this with some examples and animations. So inside the P frame, how do these motion vectors and residuals look like? So motion basically describes displacement, and the residuals captures what's left. So how does this recurrence relation look like? It sort of look like this. But the del here is residual at time t. The tau is the motion vector from t-1 to t, and I hat is the reference frame at time t1. And then then I hat t is the recurrence structure frame at time t, which is the next decoded RGB frame. So essentially, what you do is that you take the current frame, you add in you move it with the motion vector, and you add in the residual. You get the next frame. This is how typically all your video decoders or video decoding software like VLC Media Player, WhatsApp Media Player, YouTube, everything works.
Sorry, one question for representing a residual is just also RGB, or what's the?
I mean, yes. So how they are stored in the codec is DCT coefficients, so discrete cosine transform coefficients. But how FFmpeg or any decoding player works is that they take the DCT, they convert it back to RGB and add it. Right.
And if you add it, so in this space is the RGB space, or is like the DCT space?
So you add it in the RGB space.
Okay.
So they also do some, I mean, video decoding software also does some smart tricks to add it in the DCT space, then convert it back to RGB. So this is purely dependent on the how the decoding software is. VLC, for example, does a lot of smart tricks. Your typical media players do not do all these smart tricks.
Right. Okay. Thank you.
Yeah. Let's try to understand this with an animation. So as you can see here, iframe at time t, here are the motion vectors, which are just basically the blockwise optical flow. So if the motion compensation at time t looks like this, and the residuals look like this, and then when you apply the residuals, you get what is called the reconstructed iframe at time t. Here, the thing to note here is that the p-frames only contain incremental temporal information and are therefore significantly smaller in size than iframes. And how do these look like in practice? So let's look at one example. Yeah. So for this, sorry, I am not sure why. Do you also hear a sound?
No.
Oh, okay. I don't know why I hear a sound. Anyway, so here is the cooking video. So the motion vectors essentially look like these blockwise motion vectors, and the residuals are capturing essentially what's left. This is in this part of the scene. It's essentially the hand area significant motion, while the rest of the scene is static. So the residual frame is similarly sparse, capturing only the small apparent changes around the moving hand. How does it look like for our favorite hockey video? Is that we have a hockey game, which is a high motion scenario. So here the motion vectors are much denser because it has to capture the movement of the players and the camera, and the residuals are also more detailed. But even in this high motion case, both representations are substantially sparser than the actual RGB frame. Right? So the key insight here is that motion vectors and residuals are inherently sparser compared to full RGB, regardless of scene complexity. This is exactly the property we would like to exploit in video models, because even in the worst case, these codec primitives are much more compact than dense RGB frames. So before I go into our architecture and more details about our method, let me show you the clear disconnect between what Codecs gives us versus what video models, VideoLMs actually do with it. What Codecs gives us is that we have the structured sparsity. So most of the p-frame data is essentially 0 or near 0. We have explicit motion and temporal change information. And p-frames are much more compact compared to iframes in size. And what do most of the big video models do is that we fully decode everything back to RGB. We encode every frame independently with the same token budget. And we sample a fixed number of frames regardless of the video length. So this, to give you an example, open source VLMs have usually a 32K or a 64K token context window. This usually fits 64 to 128 RGB frames. For a 1 hour video, that's 0.12 FPS sampling rate, while videos like the one that is getting streamed right now, or YouTube videos, are captured at 20 to 30 FPS. So the problem is that we have excessive computational memory overhead for short videos, and we surpass the LLM context window for long videos. So natural question we want to ask is, what if we kept a natively sparse codec representation and fed it directly to the LLM? That's exactly what CoPE-VideoLM does. So here's a high-level overview of our approach, where we want to enable denser temporal coverage at a fraction of the standard token count at runtime. So just what existing methods do is that they try to sample frames and pass these frames to a visual encoder, which gives them these tokens, which goes into the video model. In comparison, what we are trying to do is that we are a codec-aware tokenization framework where we leverage the inherent sparsity and structure of these inner video codecs. So what we do is that we encode the original iframes through the standard vision encoders, but the p-frames are processed by a lightweight encoder to produce compact tokens. And then these compact tokens go into our LLM model. Okay, so let me walk you through the whole pipeline, where we replace these dense per frame RGB image embeddings with structured codec-based representation. So let's say this is your input video. So input video is obviously divided into multiple GOPs. So let's go through one GOP at a time. So let's say the first GOP has this iframe, and these are the p-frame, where one part of the p-frame is the motion vector, the other part of the p-frame is residual, and then another p-frame, right? So And then there are the multiple frames like this in the first GOP. So this is around 8 to 10 seconds of content. So what we do is we first encode the iframe with the vision encoder, right? So usually for SIGLIP, this is 196 tokens. Even for Gemini vision encoder, it's 259 tokens, right? But for the P frame, we have a delta encoder. So this delta encoder can just produce 8 tokens. So here we get a 24x less token number, so which is highly compact and a much more compression friendly compared to the vision encoder. Now for the next P frame also, we encode it with a delta encoder, and it also has n equal 8 tokens, right? Similarly for the next GOP, which can look something similar to this, where we also have again of the iframes of the P frames. We take the iframes, encode it with the vision encoder. We take the P frames and encode it with our delta encoder, which is just 8 tokens, right? And then this happens for GGOPs. Let's say GGOPs in a video. And then obviously it's the same. The rest of the pipeline is same to an LLM, where you have asked the question, tokenize the language with the language tokenizer, and pass the language tokens. So the final token stream is essentially an interleaved sequence of iframes, iframe tokens, and the delta tokens, which is consumed by the LLM. And this just allows us to enable dense temporal coverage at a fraction of the standard token count and runtime. The LLM can basically consume these tokens alongside the textual instructions without any architectural modification. So then we produce an output. So the key question to highlight here is that how can we ensure that delta tokens are aligned in the same latent space as the vision encoder? And this is exactly what our pre-training strategy addresses, which I will discuss next. So the primary difficulty lies in ensuring that the delta encoder tokens are aligned with the image tokens, because the LLM has been trained to see the image tokens. We cannot just have tokens in a different latent space. So to achieve this, we create this delta encoder as a modality adapter that enables codec-derived primitives to be compatible with the embedding space defined by the vision encoder. So how we do this is that, so if you remember from a couple of slides before, I showed you the recurrence relation where you take the iframe from the previous frame, you move it with the motion vector and add the residuals in, then you get the next frame. With our delta encoder, we exactly want to recreate this in the token space. What we do is that we take the last iframe, we encode it with the vision encoder. We take the motion vectors and encode it with just a MLP basically, because this is vectorized. So we can just encode it with an MLP. We get these tokens. What we do is that we these orange ones are the query. So with this, we do not really get any compression because this will still produce as many number of vectors. So what we do is that we pass them through a motion transformer where we have the motion tokens that were produced by the MLP, plus we append some small query tokens, which the motion transformer can attend to. And then this blue token here is actually the delta token that we would use later. So what we do after that is that we have to add the motion token. We have to move the iframe with the motion vector. So this is taken care of by the reference transformer. And then for the residual, we use a ResNet 18 to encode and exactly follow the same pipeline. So exactly follow the same pipeline, and then the reference transformer takes an input, the output of the residual transformer, which produces the warp transformer, right? Now, the output of this warp transformer, these tokens should be visually similar to the tokens of the next frame. And this is exactly what we leverage with our approach. What we do is we take the frame from the next, basically the next iframe, we pass it through the vision encoder, and whatever tokens it produces, that becomes our supervision signal. So we use this as a patchwise MSE regression loss. Now, for pre-training, we add these reference transformer and warp transformer. But for our delta encoder that actually is fit into the LLM, these transformers are not needed. So the highlighted part is basically the delta encoder, which is the MLP, the ResNet 18, and the 2 transformers, not the reference and the warp. And this becomes a token that are delta data, that is our delta token input to the LLM. And the delta encoder is lightweight at less than 15 million parameters, which is negligible compared to a 7 billion LLM that we will train later on. Just to note here is that the reference and the word transformers are only used for pre-training, because loading them during the LLM fine-tuning process or the LLM inference process means that we are dependent on the previous frame, which we are not. Then the whole point of being fast would be like sort of irrelevant, right? And this is the part that yields a substantial compute and memory reduction. So essentially, we process these p-frames through two lightweight branches designed to extract and compress codec information. Now, in the setup I just described, processing all frames at the native frame rate is mandatory, because codec primitives are defined relative to the previous frame, and skipping frames invalidate these dependencies, right? So, but do we really need to process every single p frame independently? So let's say you have this iframe and there are these many p frames. So this is, let's say, 8 seconds of content at 30 FPS. So that's 240 frames. So we have one iframe and 239 p frames. So number of tokens, let's say we have m tokens per iframe and n tokens per p frame. That means you have to process m plus 239 n tokens for every 8 seconds of content. Sure, fine-grained accent recognition may require this exhaustive temporal coverage, but most video understanding tasks can be done with sparser coverage. And that's the question we would like to ask, is that how do we actually achieve this? The answer is simple. Fuse consecutive frames together. Fuse S consecutive frames together, so that encoding the combined changes relative to a frame, not the previous frame, relative to a frame further back. So whenever we want it. This is what we call our p-frame fusion. So what we do is that with p-frame fusion, we usually fuse 30 frames together, because we want to effectively achieve 1 FPS, which simplifies this picture dramatically, right? Because we wanted to be constant towards 1 FPS, because a lot of these current video models work with 1 FPS sample. So here, instead of now producing m plus 239 n tokens, we are at m plus 7 n tokens. See the amount of reduction we get. And compared to a standard setup, which would be 240 m tokens, because you have to process the tokens for all iframes, m plus 7n is much lesser than 240 m, which is effectively a 6 to 7, a lot of reduction, right? So essentially, this p-frame fusion offers a codec native way to trade a temporal resolution for efficiency, and can be tuned to match available compute and task requirements. Just to note here is the maximum number of p-frames that you can fuse is bounded by the GOP size. Like if the GOP size is 240, you can actually fuse just 239 frames together, because fusing anything more would invalidate the codec dependencies, because then you need the next iframe. Right. Over the last approximately 22 minutes, I have established the method, and I have bored you a lot with codec primer and codec representations, right? So now the natural question is, does this representation hold up? Can compact codec-derived tokens compete with dense RGB processing for video understanding? It's time to take a look at the experimental results. So the first result we want to evaluate on is that whether the proposed delta tokens derived from p-frames provide understanding capabilities compared to dense RGB representation. This is like one of the key results to understand if codec tokens are of any value or not. So here you see 3 plots which show accuracy versus token count on 3 benchmarks: perception test, next QA, and activity next QA at varying densities. The red line is Lava video, and the blue line is our method. At every keyframe density, adding delta tokens from p-frames consistently improves accuracy while barely increasing the token count. Even under aggressive compression, for example, 1 keyframe per GOP, our model maintains strong performance with an order of magnitude token reduction. And at higher frame densities, like 4 keyframes per GOP, we not only match, but often surpass the performance of the 64 frame baseline, despite using fraction of its tokens. We see the most gains on perception test and XQA, which also indicates strong reasoning with a limited token budget. This also shows us that the delta encoder successfully captures motion and appearance cues, which are critical for temporal reasoning. Our method basically tries to preserve this fine-grained fine-grained semantics and sort of advances the Pareto optimal frontier, because you would ideally want your LLM or VLM to be here, because less number of tokens, high accuracy. This is exactly what we want. So this is sort of a critical result, because we are just with these results we show that we're not just trading accuracy for efficiency, we're generally getting better performance with fewer number of tokens. Right. So over the next couple of slides, I will show you a full benchmark comparison against a broad range of open source video models on general video question answering tasks, temporal reasoning tasks, and long form understanding tasks. So first is general video question answering. We show results first on perception test, where we are. So just to note here is that our main baseline comparison is Lava Video 7 billion, because that's the same architecture and same data, similar data scale that we train on. But we also add more models at a similar time to showcase how good or how worse we are doing. So on perception test, we're but better. On next QA, which we are a bit worse than Lava's highest token budget. On ActivityNet QA, we are much better than Lava. On Video MME, which is sort of, actually, I'm not sure if you saw, but today Video MME V2 came out. So on Video MME, the V1, this is we are very, very close to Lava Video. But here you will see that we are a bit worse in performance compared to Lava Video 7B. I will come to this in a later slide, where I will show you that this is basically dependent on the training data composition and training data scale, and not really a codec specific limitation. So essentially, what we try to say here is that with codec primitives preserve the semantic and temporal cues which are required for video understanding tasks. Just to note here is that among other codec-based approaches, we are also better than VideoLoveit and EMA, which are also validated that preserving both residuals and temporal ordering is stronger video language representation than fixed-length GOP summarize or motion-only tokenization. Now let me show some more benchmarks. So there, next up is temporal reasoning and motion understanding. This is where we would expect codec primitives to shine, because codec primitives natively capture interframe dynamics. On TemCompass, we are much better than Lava Video and other methods. Similar story again on Tomato, which both of these test action ordering, duration, and state transition reasoning, understanding of attribute change, order, speed, direction. And in both these benchmarks, our method is quite better. On CVRR-ES, which uses compositionally varied questions to expose synthetic failure modes in videos, we achieve 49.4, which is quite ahead of Lava Video's 43.6. On MVBench, we improve upon performance. We improve upon Lava Video 7 million performance by 3 percentage points. But this benchmark emphasizes pictorial semantic understanding over temporal dynamics. And the remaining gap to the top-ranked models can be explained by the fact that our base model's capacity and training data is a problem compared to what bigger models have trained on. So this explicit encoding of motion vectors and residual is a stronger temporal signal than dense RGB processing. Now let's look at benchmarks which are required understanding of extended video sequences and complex instructions. So first is Video TT. This is a benchmark from ICCV 2025, where we are actually quite good and also compete with like Qwen 2.5 and Ola 7B and Oryx 7B models. Similar story we see on Video MMU. Similar story again on LVBench, which is a long video benchmark. On long video bench, we are a bit worse than Lava Video 7B. The reasoning behind this is that on long video bench consists of questions which can be answered only if you sample that exact keyframe. And since on longer videos, we still do GOP subsampling to fit within the token budget. We miss those frames, and then it becomes impossible for our model to answer those questions. Right. So here, one point to note still is that the improvement is especially pronounced against EMA, this method, which is another Codecs-based method from CVPR 2025. Even though we train on much less data, we train on 1.39 million video question answering samples versus EMA trains on 2.4 million Codec samples. And we also do not do anything special to handle longer videos, like because EMA increases the GOP count at training time to handle longer videos. But in our case, this is the same checkpoint that works across all these different benchmarks. This results suggest that preserving residuals and explicit temporal ordering plays an important role for both instruction following and long-form understanding. Overall, compressing p-frames into compact delta tokens enables substantially more temporal coverage with the same token budget, which supports both fine-grained temporal reasoning and efficient use of the context window.
Hey, Sayan, sorry, for the last benchmark on the bottom right.
Yeah.
So you're saying the video codecs here. So maybe I think you're trying to do a blockwise fusion, right? This where you lose the keyframes, or?
Yes, also there, and also in other cases, because these long video bench consist of videos of around an hour, right? So what we do is that instead of doing frame subsampling, we do GOP subsampling. So we just take, let's say we take GOP, we subsample GOPs. So we take certain 8-second chunks. And in these certain, if the question to answer is not in the certain 8-second chunk, then we miss it, right? For Lava video, it's still it's a smaller problem, because since it samples frames, it can still get, like, if it samples that exact keyframe, it is able to answer that question. But in our case, if we take the first 8-second and then skip the next 8-second where this event happens, then we cannot really answer this question.
But I see. The current mechanism is like you fix the sampling schedule, right? It's not like by what is more important or what. There's no learning there.
Yes. We fixed the sampling. Yes.
Okay. Okay. Cool. Thanks.
Yeah, but accuracy. So what I just was saying is that accuracy is also quite strong, but accuracy is only half the story. What about efficiency? After all, one of our key claims is that codec-aware tokenization enables dramatically faster inference. Let's see if the numbers back that up. So first is we check runtime and latency, because we want to figure out if CoPE gives critical efficiency gains during inference. So we measure time to first token, TTFT, and end-to-end latency, E2EL, for generating 64 text tokens on a single consumer-grade GPU, which is an RTX 4090 at 1 FPS video input. On the left, you see TTFT comparison. So here we are 7.2x faster. Our most compact comparison is 7.2 times faster compared to Lava Video 7B, which always processes 64 keyframes. On end-to-end latency, we are around 2.3 times faster. This happens because only the iframes require full vision encoding. Both prefill time and the sequence length shrink significantly. So that's the reason why our times are so faster. Because first we have a reduced visual embedding load, since only iframes are processed by a SIGLEP, which is a 400 million model. And second, we have a shorter overall sequence length, which has to be processed by the LLM due to the compressed delta tokens. And low TTFT is quite critical for interactive user experience and essential for robotic applications requiring real-time responsiveness. And so a sub-second time TTFT is meaningful threshold for interactive applications, and our most compact comparison can achieve up to 0.33 seconds. Right? But these are numbers that are calculated on control settings, right? So you might ask a question, and then how does it perform in practice? So that's why we built interactive runtime comparison. So this is same video, same question, same hardware, different input representation. These are not simulated demos. This is exactly an iPhone app that we have built, which takes in a video and processes it with CoPE, versus takes in a video and you process it with Lava video. So here is the same hockey video where we are trying to show multi-chat question answering terms. As you can see, while Lava is still thinking the first question, CoPE is already on the third or the fourth question. And on the bottom, you also see the completion progress, where CoPE is getting completed much, much faster than Lava, while still producing accurate answers. So we are, in this particular example, we are 6x faster in speed up, and in TTFT, because we use around 20% of the total number of tokens. Similarly, another example with the same cooking video, where we are still again doing multi-turn question answering, where on the right is CoPE and on the left is Lava. And in this case also, we are around two times faster in terms of TTFT. The CoPE produces accurate answers while achieving consistent speedups at substantially reduced token counts. Few more examples, which shows that we do show this. Our model does show this consistent speedup across diverse video content. So this is an example from Friends. If you have watched the show, so where we asked Lava some questions about this episode from Friends, where Ross is asking, I think Ross is asking Chandler to be his best man, and that while you can see how fast we are. Similarly, another athletic video where this is from one of the data sets. I think this is from VideoMME, if I'm not wrong. It also sort of shows us the same thing, that we use less number of tokens and we are extremely fast. So these demos confirm that codec-aware sort of tokenization is not just semantically sound, but is a necessity for enabling fast inference. And this speedup is especially visible in the first turn of conversation, where the visual tokens dominate the prefill time. Just to point out one thing from the demos is that to maintain fairness from the second chapter, and what we did is we did KV caching, so that because all LLMs do this. I mean, if you are in a chat setting, all LLMs do KV caching, and that's why we also do KV caching, so as to be not unfair to the other methods. So then you can see that the end-to-end latency after the first turn is quite similar, but that first turn is where we shine. So another, let me show you like an impactful aspect of this was how far can these delta tokens stretch the context window. So this is because standard dense RGB sampling saturates quickly, which limits coverage as memory constraints are rapidly encountered. So what we do is that this is the theoretical scaling plot, which shows how much can we actually stretch the context window for in terms of duration. On the left is Lava Video 7B, which is a open source model. On the right is Gemini 2.5 Pro, which has a 1 million context window. So as you can see here, we are able to process 8x longer videos, right? And this benefits become increasingly significant for longer sequences because quadratic attention cost amplifies the reductions in token count. So compressing P frames into compact delta tokens does enable more temporal coverage with the same token budget, and this is a key practical advantage. Our approach allows open source video models to handle video durations that were previously only accessible to like proprietary models with million context windows. Yeah. So a few slides ago, I showed you this plot with VideoMME, and I said that I would come back to this in a later slide, right? So so here is a plot. Here is the table showing Lava Video's performance at different amount of data. Two observations. First is we are trained only on 1.3 million video QA samples, no image alignment data. And against the most comparable comparisons of Lava Video, our method either outperforms or remains on par across benchmarks, despite using fewer samples. So this says that this exactly shows that what I was saying before is that this is a our performance being worse on certain benchmarks is a data mixer specific effect rather than a codec specific limitation. This basically same data, better results. The main gap is due to training data scale and composition, not a codec specific limitation. This also underlines that structured temporal compression can yield stronger generalization even without a larger training corpora. We also evaluate on spatial video question answering because we want to answer the question is that can codec primitives capture enough geometry for 3D reasoning? We evaluate on SQ3D and ScanQA. Both of these require associating multi-view observations with 3D spatial structure. In both cases, the table shows results across different model families. Without camera poses or point cloud, CoPE matches leading models, including 2D and 3D models. The interesting part is at a fraction of the total token cost. It's 1/4 of the total token budget cost. Right. So this just shows that codec tokens also carry rich spatial signals, which can be evaluated, which can be sort of exploited. This also raises like an open question for everybody, is that can we integrate motion plus residual information directly in 3D VLMs to extract better spatial intelligence? This is a sort of a question, more open question to work for, work if anybody is interested. An important comparison we need to make is with token compression methods, because these represent the popular alternative approaches to reducing the visual token count. To tell here before that, most of these token pruning methods reduce the LLM's token count, but still pay the full image embedding cost. So you essentially, you still embed the whole image, but then try to figure out which tokens are too similar, and did you discard those tokens. In our case, our representation inherently encodes only meaningful temporal changes rather than removing any information ad hoc. And we showcase results across multiple methods: FastV, DICO, Lava, Vision Zip, and Lava Scissor. Results are clear. We do achieve much better accuracy and performance compared to these methods. All baselines in this case use 50% token budget. Our methods allows up to 93% lower token usage while being 7x faster in time in T2FT. An important point to make here is that codec native sparsity can provide a strong starting point for post hoc pruning. So in other words, our method is sort of complementary with these approaches. You could apply token pruning on top of our method for even further compression and even stretching the complex window further. Since I have a few minutes before I end, let me dissect a few design choices through ablation study, which makes CoPE work. Just to be clear here is that to reduce carbon footprint and computation costs, these ablation experiments are only trained on 60K samples on 2 days for 16 800s, so the absolute numbers are not directly comparable to our main results, but the relative comparisons are still meaningful. So the first is we do two-stage training, because we do the pre-training of the delta encoder, and then you fine-tune the delta encoder. With the LLM. The question we ask is, what happens if we skip this delta encoder pre-training and let the LLM figure out from the scratch? So without pre-training, the model must simultaneously learn codec interpretation, feature alignment, and multimodal reasoning. And that means the model basically slows convergence and weakens temporal understanding. On the contrary, when we do our pre-training procedure, we ensure that the delta tokens are in a well-structured embedding space, and the fine-tuning teaches the LLMs to fuse the I and the P frames together. So the spatially consistent pre-alignment bridges the codec and RGB domains properly. An interesting open question here is that, can we train a unified vision encoder which can take both I frames and P frames as input? So there are a few works which came out recently, like the one vision encoder from the LMMS lab in Singapore, where they are trying to train a vision encoder where they are trying to select patches based on codec information. But then can we stretch it further? Can we train a unified vision encoder which takes both I and P frames as input? So I want my siglet to take either I frames or P frames, because P frames are also sort of vision information, right? Second ablation is that how many tokens does a P frame actually need, right? So the number of delta tokens emitted per P frame controls the expressive capacity of the codec branch. Fewer tokens means that you are more aggressive. It's a more aggressively compressed representation. More tokens basically mean that the delta encoder retains finer motion and appearance cues from the codec parameters. Here, what we see is that a consistent trend moving from 2 to 4 tokens will yield a noticeable improvement as the model benefits from an expanded latent space that can more successfully capture motion and residual structure. Increasing to 8 for, yeah. Somebody asked a question, I'm guessing. Oh, okay, never mind. I thought somebody raised their hand. Never mind. So yeah, as you can see, the performance plateaus beyond n equal 8 tokens, right? And basically allocating more than 8 tokens produces diminishing returns. So n equal 8 tokens suffice. That means codec parameters are inherently very compact. Interesting future question here is that, could we adapt the token budget per P frame, so based on the motion complexity and the task requirement and the scene change, to push this even further? So essentially, let's say you always have 8 tokens, but you always do not use 8 tokens. So you can train like a sparse transformer sort of setting to be more adaptive, basically. And the final question is natural, and an important question to ask is that whether the video LLM actually uses the delta tokens, because these are very few, rather than ignoring them and relying solely on the sparse keyframes. So what if we keep the temporal structure but zero out all codec information? And this is exactly what we do. We run an inference with 1 keyframe plus 7 pframes per GOP, but set all the delta tokens to 0. So all pframe related tokens are set to 0. So this basically preserves the natural natural temporal order while stripping away all motion and residual information. So what we see is a similar structure, similar story, is that the delta tokens are getting used because they without the delta tokens there is a substantial performance drop. This means that the LLM actively leverages and meaningfully understand the compressed domain temporal cues for reasoning. It's not merely interpolating between sparse iframes, but actively uses the delta token to track motion, maintain temporal grounding, and refine fine-grained visual details. The LLM has basically learned to integrate these compact temporal signals alongside the spatial information from iframes. Yeah, so I'm at the end of my talk. I think this has been I've presented most of the results. If you're interested in our bit more detailed results with ablation studies, because there are certain ablations or certain design choices which made CoPE work, and which is also, I think, why CoPE worked on a larger scale compared to some other methods which also tried Codec before. So you can check out the paper. But let me summarize the key takeaways of this work. So first is codec-aware tokenization is sort of a practical and efficient foundation for future video models. Codec primitives are a natural fit for video models, right? Codec primitives natively encode these motion vectors and residuals. There's no reason to discard the structure and reprocess everything as dense RGB. We see massive efficiency gains with competitive accuracy, 93% fewer tokens, 86% faster TTFT, and also maintaining performance. And we do this evaluation across 14 benchmarks. And we can also do more evaluation on other benchmarks in a newer version, which we would push out in a couple of months. Moreover, the approach is general and scalable. We use standard transformer components, no architectural modifications to the LLM, and this approach has applicability beyond video question answering, like just beyond question answering to robotics, to retrieval and 3D understanding. We already saw 3D, but we haven't touched retrieval or VLA models at all. In essence, decades-old video models, video compression meet model language models, and the combination is sort of remarkably effective. Right. Let me leave you with a few limitations and future work, which could be interesting if anybody is interested in this domain. That we did not add support for B frames, which are bidirectional, because B frames, like P frames, depend only on the previous frame, but B frames depend on the previous frame and the next frame. We did not use it because P frames have complex causal dependency, and that would mess up the LLM. But can we still leverage B frames in some other way? One option to address this would be to use the decode order instead of the render order, basically. And can we directly operate on the sets of blockwise motion vectors and the quantized GCD coefficients, so that we can directly take encoded videos, not even take motion vectors or these residuals like images. We directly take the blockwise motion vectors and GCD coefficients that are getting encoded, right? Second, and lastly, the fixed fusion window that we use is suboptimal for videos with varying motion. Can we use motion and content adaptive fusion to improve both efficiency and accuracy? I think this is quite interesting. Additionally, we can explore sensitivity to codec type, bitrate, or encoding how much quality to further validate our approach. Thank you very much for your attention. Happy to take any questions.
Thank you. It's very good presentation. Thank you so much. Any other questions from audience? Right. So I think one question I have is the when you train the delta encoder, right? I guess two questions. Like one question is like you only use reconstruction for the training objective, right?
Yes.
So that maybe that's possible. The network will ignore some like motion signals or from your P frame. So
why would the network ignore some motion signal? Just asking.
Yeah, right. for example, here, right? Like, so the network's objectives is just trying to reconstruct the next frame, right?
Yeah.
So maybe it doesn't learn too much like semantics or highlight for the you know the moving parts, right?
Yeah.
So I wonder whether you can, I don't know, just some random thoughts, right? Like you can integrate other objective to encourage the network to use those information.
Yeah, I think that is a valid question, and I think that is important. So we could specifically ask the network to learn more motion or residual information. So here we are basically treating it as a residual, we are treating it as a reconstruction objective, like a Japanite like objective. But we could explicitly have supervision signal where we ask the network to learn the motion or learn what has changed. I think that could be even stronger signals.
Yeah, that's right. That's right. And the second.
Yeah, I just want to interject. Sorry. So I think that this is nice because like it works well with the video language model at the end using these tokens, right? Because it's like they're just representing each intermediate step.
Yes.
Oh. Okay. So you don't have a question? Just comment.
Yeah.
Okay.
But
yeah.
I mean, adding those, adding extra super to add to Atharv's comment is that to add those extra supervision signals, we would still be in the same space. I mean, we would still not lose the video LLM space, like the space that the LLM wants these tokens to be in, right? But those could also, those signals could also help improve the delta encoder and make sure that it's trained properly, right?
That's right. I guess my second question is about the, so I think right now you're mainly trying to verify what this encoder learn using like language tasks, right? Like what if you directly just use those tokens for some, I don't know, like visual tasks like robotics?
Yeah, right. So that's a good future work, because like how do you, like, let's say, can you solve video retrieval? Can you solve these image matching tasks, like robotic tasks? Can you solve these tasks directly using these tokens? I think that's a very good question to answer. And also, I also believe that for those tasks, the amount of compression we get is not compression is not the main thing that you are trying to address there. You're trying to basically like in our project, like we focused mainly on the compression bit, but in a robotic task or a retrieval task or a video like more image matching task, right? The ask is to get better accuracy, better performance. I think in that case, that's a valid task, and we could also use like more tokens to get more and more understanding, right? And you could still use the similar robotic supervision or image matching supervision that people usually use in these cases. I think that's a valid extension of our work, and that could be really interesting to see.
Yeah. Very cool. Yeah. I think. Yeah, if that's all the question, and thank you, Sayan, again.
Yeah.
I will share the recording later. Yeah, thank you.
Yeah, I can also post a slide from the chat.
Okay.
Yeah. Bye-bye.